Good afternoon, everybody, or good morning or good evening, depending on your time zone. My name is Laurent Polidori. I'm the president of ISPRS Technical Commission 3, Remote Sensing. And on behalf of ISPRS, or the International Society for Photogrammetry and Remote Sensing, it's my great pleasure to introduce this webinar. Second webinar on land use, land cover change detection, organized by our colleague Patricia Mwangi from Kenya, with the support of the ISPRS Student Consortium. So just a brief introduction to say thank you to our two speakers for accepting this invitation to participate. And I want to recall that this webinar is organized in the frame of one of the working group of Commission 3. Commission 3 dedicated to remote sensing. It consists in 12 working groups dedicated to the different aspects of remote sensing, both technological, like algorithms and sensors, or application-driven, like land use, land cover change detection. And I would like to take this opportunity to welcome all of you to join the ISPRS working groups. So in particular, in this case today, we are referring to working group 4, dedicated to land use, land cover change detection in Commission 3, so remote sensing. So please go to the ISPRS website, the Commission website, and have a look at it. Patricia Mwangi is the key person at the moment, and we have the opportunities in the next 2 years to join around collective publications, webinars, and so on, or special sessions in different events. So please, beyond this particular webinar with the 2 very interesting lectures, don't hesitate to participate in other opportunities to the different activities which are being proposed in the frame of these working groups and others. So I don't want to be longer, and now I think it's time for Patricia to present the objectives of this webinar and introduce our 2 speakers. So please, Patricia, the floor is yours.
Okay, thank you very much, Dr. Laurent. Good afternoon, good morning, everyone. Thank you so much for joining this webinar. The webinar is organized, as you've heard, by the working group 4, which mainly deals with land use, land cover change detection. And today we'll have 2 presenters, that is Dr. Yoksa, Mshelia, and Dr. Mahlatse. And they will each present different projects and also application areas, even dealing with AI on land use, land cover change detection. So our first presenter will be Dr. Yoksa. A brief about Dr. Yoksa: he's a research fellow at ARIN, African Research and Impact Network, and his research mainly focuses on climate change, urban planning, and ecological modeling. And his work aims to inform sustainable development policies and enhance urban resilience in rapidly growing cities. Today, his presentation is on modeling the spatial dynamics of land cover transitions and vegetation conditions in Abuja City, Nigeria. So if you have any questions for Dr. Yoksa, kindly type them in the chat and I will read them out for him. And Dr. Yoksa will also leave his email for if you want to get in touch with him. So welcome, Dr.
Thank you, Dr. Patricia. And I want to thank the ISPRS Consortium for the opportunity, and want to appreciate each and every member that have joined to participate in this seminar. I would like to start with my presentation. Kindly wait, I share my PowerPoint. Okay, this is the title of my presentation, which is, as Dr. Patricia have said, modeling the spatial dynamics of land cover transition and vegetation condition in Abuja City, Nigeria. My name is Dr. Yoksa Mshelia, a research fellow in African Research and Impact Network. Globally, as we can see, this trajectory of population growth has exceeded 50% as at now, and it is projected that by 2050, it will exceed 70%. which 80% will come from Global South, which includes Africa, Asia. This raises a concern for the planning to achieve United Nations Sustainable Development Goals. Globally, land cover have been transformed. 32% of the land cover globally has been transformed between 1960 to 2019. This has resulted to land degradation, increased vulnerability of climate change. Thereby, understanding land cover change is crucial for urban planning and development for resilient cities. Change detection and climate and ecological modeling, which includes GIS remote sensing, helps in collecting, visualizing, and analyzing satellite imageries for detecting land cover dynamics globally. Hybrid models such as CA Markov, clues, and also the Markovian chain are widely used for accurate land cover predictions to be able to determine the possibility of land use transitions into other land uses. This study aims to assess the dynamics of land cover transition and conditions in Abuja City since its establishment as the capital of Nigeria in 1990. As we can see projected on the screen, this is the map of Abuja City, which is located at the center of Nigeria and the semi-arid region of the country. These are the materials that I've used for this study. Landsat imagery, administrative boundary areas, which I collected from the Abuja Geography Area Council, land cadastral zones, urban center, roads, networks, and rivers. DEM also from United States Geological Survey and CGPS. All this data will be utilized in modeling and analyzing the land cover in Abuja City. This is the methodological flow of the study. The Landsat imagery first will be processed by random forest classification to produce the land cover types, and also produce NDVI, which will be processed and also analyzed using Mann-Kendall trend test and also Theil Sen slope estimator. For the prediction, hybrid CA Markov will be used together with the locational factors and also the longitudinal factors to predict the land cover for 2050. So first, I will start with the dynamics of land cover transition. This is the methodology specifically for the land cover transition. I started by classifying the land cover using random forests in Google Earth Engine platform. These are the satellite classification and sample points for the land cover classifications. Landsat 5, Landsat 7, Landsat 8, Landsat 8 also were used for the year 1990 all through to 2020. The sample points that were collected all above 2,000 points for each of the year. This is the visible representation of the sample points that were collected. Accuracy assessment was also performed for the random forest classification to ensure that the classification the reflectance were actually captured accurately and meeting the criteria for post-classification and comparison, which is the next stage. The hybrid CA Markov modeling was done in TerraSet software. The model setup was performed to be able to acquire the criterion weight determination by AHT method, and also to develop the locational and topographic factor. The locational and topographic factors are urban center, which is the first at the top, and at the bottom, then the slope, which was derived from DEM, and railway and distance to built-up and distance to the road were also developed using Euclidean distance from ArcGIS software. So, however, the transition constraint variables were developed in TerraSet because of its ability to be able to restrict expansion into those areas which are protected areas, built-up areas, water body, and waterways. Those areas have been determined as a parameter to restrict development of urban areas. This is the model calibration, the transition probability and area matrix. which was performed in Cellular Automata, the other component of the Markovian chain. So it was processed to be able to determine the transition of each land use from one land use to the other, and the potential of one land use decreasing or increasing. Model simulation and validation. This is the comparison. The model, the 2020 land use was predicted using the 1990 and 2001 land use to be able to determine and see if the model can perform a prediction accurately. And the result for the prediction shows for 2020 shows that the consistency is over 83%, while the inconsistency area was 17%. And as you can see, the categorical image comparison shows that the KNO and is above is 0.86. All the parameters that were measured shows that all the accuracy were above 0.8, which is actually good and valid, and which now would allow for the prediction of 2050. Now the results for the objective 1. Extent and rate of land cover change from 1990 to 2020. Visually, you can see that the built-up area has been expanding, has been increasing from 1990 to 2001 to 2014 to 2020. By 2020, as you can see, the built-up area is more dense and has occupied more space than any other land uses, which indicates that other land uses have been reducing. The extent of land cover also, this is the statistical representation. The kappa was between 0.85 to 0.90. So as you can see, by 2020, built-up areas has increased by 39.55% at the rate of 4.2% per annum, while other land uses have been declining consistently, accounting for 24.7%, 8.16%, 6.64%, which represent agricultural land, vegetation, and bare land, respectively. Vegetation also declined at the rate of minus 3.15 per annum. This is a transition matrix, which shows which land cover transitioned from one land use to the other. As we can see in the result, 23% of agricultural land, 7% of bare land, and 12% of vegetation have been converted to built-up areas. Built-up areas exhibited the highest persistence. As we can see, it existed by 11.95%, which shows built-up has been consistently increasing, not decreasing. The prediction result, as we can see here, shows that accessibility to road networks and proximity to urban areas are the major factors that contribute to built-up areas increasing, or will I say concentration of built-up. People mostly prefer to build near existing buildings or urban areas or road networks. So now vegetation, assessment of vegetation condition. The assessment of vegetation condition was done using Mann-Kendall test and 10 slope estimator. This is a result for the assessment. As we can see, there is a significant decline in vegetation density from 1990 to 2020. As the parameters below, you can see that degradation of degraded areas are over 256.44 kilometers, while areas that have improved are just 83.81 kilometer, which shows that 46% of the whole area have really undergone degradation, while 15% has improved and 38% remained stable. Higher NDVI value indicated higher density area, which earlier I said declined from 1990 to 2020. So in conclusion, this study have determined that geographical information system is very vital and critical tool in urban planning because it helps urban planners to make decisions, improve communication, and create more sustainable and resilient cities in the future. Just as the prediction result has indicated, it allows for urban planners to look at the output and also determine areas that needed further restrictions for green areas to be developed as well. Here are the recommendations. Enforce implementation of policies that promote efficient land development and green space building techniques to balance urban growth and green space preservation. Regular monitoring of land use changes, vegetation health, temperature patterns support evidence-based decision-making. Vegetation density should be integrated into development control framework, with green space volume being an important variable in urban development. Also, green space design strategies be made an integral part of urban development that creates large connected green spaces with percentage over specified in zoning policies, as urban heat island is a spatial temporal phenomenon. I would like to acknowledge these organizations for their support. Thank you.
Okay, thank you very much, Dr. Yoksa, for that presentation. It was very interesting. Kindly feel free to put in your comments as well as any questions on the chat. I have one question for you. When you were doing your modeling for Theil 2050, what were the major challenges you may have encountered?
Okay, the major challenge that I've encountered in the prediction was basically identifying the constraint and the variables that and the suitability variables that would determine the expansion of land uses. So what I did actually, I developed a questionnaire. I met experts in the field, got their input, experts in urban planning in Abuja City, because I feel every other city have a unique characteristics of expansion also as well. And also, so I was able to get from Abuja Geographical Development Agency, the agency that manages the urban planning in Abuja. So I was able to get the information from them and input, and then also I then ran it through the AHT, that's an analytical hierarchy process, to see which one it will impact urbanization, will it impact the expansion of urban areas more, and which one would constrain it. And also, some of the challenges that I encountered is, one of the challenge actually is the availability of data. When it comes to the spatial data, the Landsat data is the accuracy. The pixel size is huge, and it's not as accurate as that of others like Aster. So I would suggest that if other people that would use for prediction, I would suggest that Aster is a very good would be a very good data to be used.
Okay, thank you very much, Dr. Yoksa. Please put in your chats, your questions in the chat, and Dr. Yoksa will be able to answer them. And also, as well as your email. I can see a question has come. Bravin is asking, in terms of your research, did you encounter water-sensitive policies for urban design in place or plans? Since within the presentation, I noticed you advocating for environmental sustainability in terms of greening.
Well, I did not encounter any challenge in terms of water sensitivity policies, although areas that were gazetted as water zones and also water bodies, I mapped them out, and then also I then made sure that they are now included as the areas for constrained development. Those are the strategy I used, because adopting from other previous studies, such approach usually requires, yes, an existing policy, but also the gazetted areas are the main concern because areas that have been proposed also for, let's say, dams, also are areas that should be adopted and also be highlighted as constrained areas so that no development can cross into it and also cause, will I say, development into water bodies, while it won't represent the prediction very well.
Okay. Another question by Leroy. With your expertise on sustainable development policy creation as a research fellow at ARIN, I have thought about GIS Needs Assessment Kenya, July 2017, and experimenting with custom base maps in QGIS by overlaying topography layers from trained open data. If we had unlimited resources, would data or models, I think, help you prioritize in supporting urban planning decisions in these areas?
Absolutely, absolutely. It will actually be helpful. It will actually be good if such will be implemented and experimented. But based on the GIS needs assessment of July 2017, I wouldn't comment on that as per se, but I would say that utilizing those base maps would actually contribute significantly, because if you can see from my prediction modeling, I've used topographic layers to contribute to the model's performance.
Okay, thank you. I think I just have another question. Which would you say that there was any particular variable that you found would weigh more compared to the rest that you were using in your analysis? Any variable?
Variable for the prediction?
Yes.
Okay. I feel from the criterion that I've used to measure the significance of the variable over the others, urban center seem to pull more development than the other variables, and then followed by major roads. The major roads development tend to concentrate by the major roads as well, then followed by other existing built-up areas. The last amongst the variables that did not perform as much as the others is, let me say, train station. It was lesser than the other variables.
Okay, thank you very much, Dr. Ari, for your time. Dr. Yoksa will still be in the presentation for a while, and he will respond to any questions. Right now, I'd like to present or invite our next presenter, who is Dr. Mahlatse. Dr. Mahlatse is a lecturer at University of Johannesburg, and his recent work focuses on advancing the use, understanding, and implementation of cutting-edge remote sensing technologies and machine learning models for agroecological systems research and application development. He's been involved in very many projects, and some of them, there's a link that is there if you want to read more about the various projects that he has been involved in enhancing food security in African agricultural systems. And currently, the presentation that he will make is on global to local scale landscape evolutions through multi-source satellite data and artificial intelligence. Welcome, Dr. Mahlatse. Kindly, Dr. Yoksa, kindly, could you stop sharing your screen?
Am I still sharing?
No, it's fine.
Okay.
No, it is okay. I think as we wait for Dr. Mahlatse to join in, I can probably still be reading his brief profile. Dr. Mahlatse has worked for nearly a decade at the South African National Space Agency as a remote, that's SANSA, as a remote sensing scientist. He has extensive expertise in machine learning application, image analysis, multispectral and hyperspectral, spectral analysis, that is near infrared to mid-infrared range, land cover or land use mapping, agricultural cropland extraction, and statistical and spatial modeling of landscapes. So he is yet to join in, but a little bit.
I think he's here. He is in mute
Yeah.
mode. So can you please unmute yourself?
Hello, thank you very much. Thank you, Patricia, and hello, everyone. I'm very much happy to be here, and thank you for the invitation. So, as introduced, my name is Mahlatse Kgyanyago, and I work at UJ. So, I see messages that my internet is unstable. Please, if I'm not clear, let me know. But as introduced, I've been applying Earth observation and machine learning to derive information on land cover, land use, and agroecological systems for many years now. I started at South African National Space Agency, and I recently joined the university 2 years ago. So I've been developing products on band area monitoring as well. Cover just the background, land cover and land use. Then we cover the remote sensing of land cover, land use, and the global land use cover changes, looking at the case studies as well as the challenges, and also look at some of the progresses and the future of land cover change analysis. So let's get into the webinar. So we know that one of the critical or the biggest problem that we have today is climate change and climate variability, where some of the areas are receiving too much rainfall, and whereas other areas are receiving very little rainfall. So this results in crop failure as well as insect pests, and this really affects the food security, because disasters, climate-related disasters such as droughts have been reported to cause drought, and we have seen a lot of cases of outbreak in most areas and affecting productivity of the land. And this is amid the greatest challenge that you also have, particularly in developing countries and sub-Saharan Africa, on hunger, malnutrition, poverty. So about 30% of people that are severely food insecure are actually located in Africa. So these affect food availability, affordability, and access. So we also have disasters such as wildfires, also invasive species, bush encroachment. All these things affect the productivity of the land. And for example, the wildfires are also responsible for tree mortality in the forests, habitat loss, changes in ecosystems, greenhouse gas emissions, alterations of local weather patterns, biodiversity loss, as well as reduced carrying capacity in areas where livestock farming is practiced. But we also have another challenge of potable water. And we have seen throughout many years that climate change is causing most of the lakes and the dams and rivers to shrink and the flow rate to decrease. Other impacts on our activities on the environment are actually stemming from the humans or human activities, such as deforestation, mining, land management practices, such as grazing intensity that are often pushed by disasters such as droughts and poor land management practices. And you also have agricultural expansion as a result of trying to feed the exponentially growing populations across the world. So all these factors are causing rapid changes on land cover and land use. And you also have a lot of population that are migrating from rural areas and moving into the cities and causing rapid urbanization and also reducing the resilience of most cities to disasters. So in response, the global policy frameworks are trying to curb most of these impacts that are coming from climate change as well as human activities. So one of the critical goals is goal 15, life on land, which seeks to protect, restore, promote sustainable use of terrestrial ecosystems, sustainably manage forest, combat desertification, and halt and reverse land degradation and halt biodiversity loss. So some of the statistics that are published by the UN is that 100 million hectares of healthy and productive land was degraded every year since 2015. And some of the statistics as well is that protected area coverage has halted since 2015. So there are other goals as well that are related to our topic today, such as sustainable cities and communities, as well as climate action. So all these factors, as I've mentioned, are impacting land cover and land use. So just to describe what these terms mean going forward is that land cover describes the main type of natural ecosystem that occupies an area, either by vegetation types such as shrublands, grassland, forest, or other biophysical classes such as permanent snow, bare land, and water bodies. And if you look at the land use, then we are referring to how humans modify or exploit an area. And this come in a form of urban areas, as well as agricultural fields, and all the other types of land uses that you can think about. So there have been multiple sensors that have been launched since the 1970s, starting with the low resolution satellites such as AVHRR, MODIS, but also the critical milestones in all of this is the launch and availability of Landsat missions, which provide medium resolution data since 1972. So this data started with Landsat 1, and currently now we have Landsat 9 and Landsat 8, which are still operational. Adding to this and in continuation of these missions, we have Sentinel-2 data, high-resolution data, twin satellites that provide 5-day repeat cycle in most areas. Apart from this, then you have other Copernicus missions such as Sentinel-3 and Sentinel-1 radar satellite. We also have other missions coming from China, Brazil, missions such as CBAS, CBAS 4B, and all these data sets, ample data sets, provide us an opportunity to actually be able to map land cover, land use, as well as how it changes over time. So just an overview of some of the progresses that have been made in terms of land cover mapping. Starting with the global data sets, we have what we call world land cover, which is a data set that is generated from MODIS satellites or MODIS sensors at 500-meter resolution. So on a global scale and annually, MODIS is, NASA is producing this land cover type information in several classes. So apart from the classification system that is displayed here, they provide multiple classification systems, including the IGBP, International Biosphere Program, as well as University of Maryland Land Cover Classification System and FAO Land Cover Classification System. Apart from that, they also provide plant functional types, leaf area index, as well as biome geochemical cycles. So from just one data set, you can be able to derive multiple land cover data set based on different land cover classification schemes. We also have the Copernicus Global Land Service land cover at 100 meters. From my knowledge, the data started from 2015 up to 2019, and is also based on the FAO classification system. And this is very detailed land cover classification system, which characterize different vegetation types, as well as the land uses. So the data has been generated at about an accuracy of over 80% globally for both the 2015 and 2019 years. And this is one of the only data sets that has met the CEOS, which is Committee on Earth Observation Satellites, Working Group on Calibration and Validation Land Product Validation, stage 4. So this means the product has been validated in various areas, and yeah, it's one of the few global products that have been validated at this level. So in terms of land cover change, normally, there's also a product that is coming from CGLS, which is based on this change scheme, where on this side you have the from date image and the change into image, and then they cross tabulate the classes between each other, and the diagonal classes would indicate the areas that event change. And for example, with forest, then it converts to other vegetation, wetlands and bare, then that is deforestation. And if it converts to cropland, that is deforestation and crop expansion. If it converts into urban areas, that is deforestation and urbanization. And then in rare cases where it converts to water, then that's water expansion. So there's also other products. I'm not going to go into details in terms of what they are, but I also wanted to share this global land cover product and the platform that has been developed by Copernicus. And as you can see, you are able to interact with the platform with various land cover classes. And you can also produce some statistics of the area coverage of these land cover classes. You can compare between the different years, toggle between the different years, and see how the land cover has changed. Apart from that, you can also download the report to your own machine and be able to integrate it with other reports that you might be required to do. So for example, you can see the bar graph, which also indicates the area as well as the percentage coverage of that particular land cover over Kenya. So you can see that this is a very detailed land cover. product, but you can also view the land cover changes, as I've mentioned before. You can see land abandonment, desertification, wetland degradation, urbanization, and so on. So this presents a very detailed land cover change classes. And you can also go into specific areas like cities or districts, and you can compare across different countries how land cover has changed. So for example, you can look at Kenya, Nairobi versus Gauteng in South Africa. That's where I am right now. And you can switch, compare year to year, the same year, and look at the annual changes, and also be able to generate the report. So you can see the areas for Kenya and Gauteng, Nairobi and Gauteng. Of course, they are two different, but you can be able to get some appreciation in terms of the area coverage in these two mainly urban areas. And of course, again, you can download the report and visualize it and integrate it with other reports that you have. So there's also other global land cover data sets such as the Climate Change Initiative, which has been aimed at for land cover change analysis as well as climate modeling, particularly to meet the GCOS, which is the Global Climate Observation Initiative. And you can see how detailed the land cover is. And also there is also a move towards a higher resolution land cover products. One of them being the ESA's African land cover, which is provided at 20-meter resolution. So this also follows the UN FAO land cover classification system and is building on other previous land cover products by ESA and Copernicus, such as Globe Cover, GLC 2000, and Globe Albedo and Globe Corin land cover. So they're drawing on that experience to build some of these detailed products that we see today. So just to look at some of the global land cover change case studies, we'll look first at this study by Radwan, Global Land Cover Trajectories and Transitions. So the problem is significant human-induced environmental changes from local to global scales are occurring at a rapid rate. Anthropogenic land cover changes threaten sustainability of ecosystem services. Major land cover changes include urbanization, agricultural land loss, agricultural land expansion, deforestation, afforestation, and desertification. These changes can have detrimental impact on both the environmental conditions as well as human activities, particularly food security as well as economic development. So there is a need for a comprehensive understanding of the gains and losses in land cover types, including the magnitudes, the locations, the timings, transitions. The aim of the study was to characterize and interpret historical land cover changes that occurred across the entire globe, as well as to analyze the variability of land cover dynamics between and within the Earth's continents over 27 years time frame of the ESA CCI land cover dataset. So some of the results that they obtained is that total area of the gains and losses of the different land cover types was found across the globe between 1992 and 2018. And as you can see, there are gross gains, some gains in agriculture, forestry, natural vegetation, and some losses in declines in bareland, natural vegetation, forests, as well as agriculture. And you can also look at the net change when considering both the gains and losses. You will see that agriculture has increased as well as urban areas. So they went on to look at the changes per continent, and you can see over Africa, the net changes as well includes increase in agriculture, increase in forests, and some decline in natural vegetation, increase in urban areas, decline in bare land. So Asia as well has experienced the largest net gain, contributing to about 45% of the global gain in urban areas. And South America had a large net increase in agriculture and a large net loss in forests. So from this figure as well, you can see how land cover changed or transitioned from one land cover to another. Natural vegetation, about 13% of it converted to forests, and forests, about 1% of it converting to urban areas. Agricultural lands also converting to urban areas. So you can see already that this has a huge implications on food security as well as biodiversity loss, deforestation, and carbon stocks as well. So these are some of the maps that were generated, zooming in specific areas. And the main land cover type responsible for substantial forest cover losses was agricultural land in most of these areas. Therefore, agricultural land experienced substantial gains ranging from 7% in Argentina, 64% in agriculture in Bolivia, 85% forest loss in Liberia. And these are same maps in another area where you can see a growth in urban areas. The major take-home messages is that the release of the ESA's CCI land cover global dataset has enabled a step change in understanding global land cover changes that have occurred over a period of more than a quarter of a century without significant spatial resolution trade-offs. The results also show that the ESA land cover can provide valuable insights into land cover trajectories, transitions, and the locations of the changes at global, continental, and national scales. The COSA spatial resolution, which was part of making the product, especially in the earlier years, may pose limitations on the data from those earlier years in the series when you're doing the change detection. So it may be preferable to collect reference data from several other years in order to derive the accuracy assessment from those years. So another important thing to note is that the accuracy of the land cover products has a huge impact as well on the land cover change detection that you do based on those products. So therefore, it's very important to always look out for the accuracies of these products, especially the global products. So I'm going to skip this case study in the interest of time. We can always share the slides, but I wanted to move to the progress that have recently been made, particularly an attempt to start creating high resolution global land cover datasets, particularly the first product that came from, which was an effort from China, based on Landsat thematic mapper and enhanced thematic mapper. And later on, it was improved with Sentinel-2 and Planet dataset. So the earlier product, these are the general steps that you would actually follow when you are doing land cover classification. But the important thing is that the authors evaluated multiple machine learning and traditional algorithms or classifiers, and they were able to achieve these levels of accuracies for different classifiers. So the MLC is the maximum likelihood classifier, which is a traditional classifier, 53%, well, almost 54%, and decision tree, 57.9. Random forest, which is a machine learning algorithm, achieved close to 60%, and support vector machine, also a machine learning algorithm, achieving about 65%, which was the highest among the compared algorithms. But the concerning factor even though the product is high resolution, when you look at the country level accuracy matrices, you'll see that they are quite low, right? So although the product itself achieved about 65%, but if you look at most of the African countries, particularly South Africa and most of the Eastern Africa, achieved less than 50% in terms of accuracy. So this essentially means that even if we can appreciate the high resolution that is provided by this particular data set, but if you are looking at analysis at a very detailed level, you are actually going to incur a lot of inaccuracies in your analysis. So they later on went to improve the product using Sentinel-2 and the latest Landsat dataset, as well as the Planet data. And you can see the level of detail that was achieved from this improvement. So they were able to map in most of the years, starting from 2000 up to 2021, the accuracy was closer to 80%. And in some of the years, particularly after the Sentinel-2 became available, the accuracy actually improved. And this was implemented in the cloud computing platform called Google Earth Engine, and using temporally dense land cover or satellite images. So this is another product called ESA World Cover Dataset, which was generated for 2020 and 2021. And this is a platform which you can visit as well to look at the changes that occurred in between the 2 years and the level of detail that is actually provided by this product at, I think, 20 meters as well. So another popular product is the Esri land cover product, which was generated based on an AI algorithm based on neural networks, convolutional neural networks to be specific. And you can see the accuracies have improved quite a lot. This data is at 10-meter resolution, and we can achieve up to 85% accuracy. And this was tested in various countries. So an interesting study looked at the comparison of these high-resolution global land cover data sets. And you can see the distribution of the validation data and the compared world cover data set coming from Copernicus, which was generated using machine learning algorithm called gradient boosting decision tree, and dynamic world land cover, which is another groundbreaking product generated from convolutional neural networks, and Esri land use land cover, which was generated with a deep learning algorithm. So their results show that the world cover was the best performing product, achieving over 80% of accuracy in most regions, followed by the dynamic world, and Esri was the least performing in most of the countries. So you will notice that, the Esri land cover is one of the accessible products because people are using ArcGIS and it comes standard with it. So it's easily accessible. However, it's always important to note these inaccuracies in the land cover products. And also the product has been, for example, for Africa, to be specific, the ESRI reports 85% accuracy. However, this has not been validated in Africa, for example. So if you check the local accuracy, then it could be a different story altogether. And then if you look at the spatial characterization of different land covers, well cover at 10 meters versus when you're looking at very high resolution image, you'll notice that well cover kind of characterizes land cover much better than the other two products, but ESRI is the worst one. Some of the challenges, particularly when you're dealing with this global land cover data set, whether they are coarse resolution of high or high resolution, the challenges is that they achieve good global overall accuracy, but they are achieving relatively low accuracy when you consider landscape scale. There's poor spatial representation at landscape scale. There's too generalized classes, which limit the support of many change analysis applications. There is poor representation of fallow croplands or other temporally changing land covers and land uses. For example, the fallow lands are often classified as active lands, whereas they are probably should be under herbaceous class or something like that. Therefore, it is important that we integrate multiple data sources and not just rely on one sensor so that we can enhance the accuracies of land cover classifications. And also, there's poor characterization of heterogeneous landscapes, which really affects the representation of the land cover types. So within South Africa, we have been generating high resolution land cover data sets since 1990, and this achieves an accuracy of about or above 80%. And these are some of the results, just rushing through it. But we also produce a very detailed land cover classes and different classification schemes as well, which can be collapsible to general classes as well. So in total, the highest or very detailed land cover product provides about 73 classes, which is very, it can support many applications. So this product can be also accessed via the Google Earth engine in a cloud environment. So one of my students also used the product to assess land degradation and using the Trans-Earth tool within Quantum GIS. So the first step is to define what is degradation, and then they classified between 1990 to 2014, 2014 to 2020, and the long-term changes as well. So you will notice most of the areas in this basin, Moda River Basin, have experienced degradation. So the data has also been applied for enforcement monitoring. You'll notice this area is proclaimed as a protected area, but the farmer, the person, the landowner is actually farming inside it, which is an illegal activity. You can use the product for soil carbon mapping, for reporting for RED++, for tracking erosion, and land cover, land use changes. So I just wanted to rush to some of the latest developments. So these are enabling factors, particularly noting that you do not need the large computer anymore to be able to do some of the analysis because of the availability of cloud computing platforms such as Digital Earth Africa, Dania platform, which became available recently, as well as Google Earth Engine. All these are provided for free for most of the research purposes and experimentations. And they are well integrated within open source software such as Quantum GIS. So one of the interesting trajectory in terms of this science, land change science, is the integration of large language models such as your ChatGPT, where we are seeing new studies looking at image interpretation. So the user will put a command and the model will actually give you interpretation of the land covers. And then in the future, I would envisage that we will be able to assess how much area, ask the model how much area has changed, plot the changes, write a report, what are the main land cover transitions. And these large language models have been well trained to an extent that they will understand the user's requirements and be able to comprehend the intentions of the user and be able to provide those results. This will really increase the accessibility of the usage of remotely sensed land cover dataset and land change dataset in order to inform policy making, decision making, because currently I still feel that the data is not very much used. So these are some of the latest developments where you can ask the algorithm multiple questions, and in the background, it can be able to make these computations and give you the results. Thank you very much. Sorry for being over time.
No, actually, you're quite on time. Thank you very much, Mahlatse, for that very intriguing presentation and various application areas. For probably someone who was very curious, the question was, for these global products that you showed us for land cover,
Yeah.
are they freely accessible, or do they need to, the question is whether it's freely accessible for them?
Yes, they are very much accessible. So they are, you can download them or interact with them on the online platforms for most of these products.
Okay, thank you. And I've seen one thing that would be very important based on the various applications is that it's critical before an individual gets to use a certain product is to look for, would you say that probably one of the criteria for you to use a certain global product is to first look at the accuracy? That would be their basis. If it's, what would be the threshold for them to use, for example, to look at it, and what applications?
So generally, it depends at what scale you're looking at, right? And level of detail that you're looking at. So generally, anything that is above 75% is acceptable, but this also depends on area to area, right? For example, people in conservation might need very detailed classification scheme and higher accuracies for those classifications, particularly because this information, they want to use it on an operational basis and to inform policies. So you don't want to quantify or make huge errors in those reports. So 75% is generally what is acceptable for most of the applications, but this will vary from application to application. So this, for example, if you're analyzing forest change at a landscape level, for example, for plantations and so on, those people, they want to check or detect as early as possible when there is poaching of the trees and so on. So you need a highly detailed data set and very high accuracy in those cases. And then if you're looking at the more generalized country level analysis, anything above 70 again is still very good for most general applications, and you might not really need as many classes.
Okay. So another question would be, would the level of accuracy, has it been defined per region, or would it be like the overall data set? For
So most of
example,
the
if someone is working in, Sorry.
Yeah,
Go on.
please go ahead.
The question was if, for example, I'm working in Kenya or I'm working in Ethiopia or another country, the whether there'll be a difference or a level of accuracy that has been well defined.
Yes, so what the users must always look out for is the validation reports for each of these land cover products, particularly global land cover products. And then you check how the data was collected, what is the representation of the validation data over your country, right? Because at a global level, or maybe the validation of these products is dependent on, for example, crowd sourcing of the data set, and then they might not, and also as well the partnerships that the product developer has within different countries. So they might not have very good validation data over your country. So it's always important to check the distribution of that validation data over your country and how much accuracy. So most of the time, if it's a global, they give a one number to say the global data set provides, say, 90% accuracy. I wouldn't trust it to apply it at a country level, for example, without validating that data before. So one of the things that you can do as well is to validate the data yourself by collecting your own validation data. There are different crowdsourcing platforms, which I had skipped in my presentation. So an example is this Collect Earth platform, which provides
the amount of land they use, and
it provides the users with the capability to collect the validation data sets from aerial imageries, high resolution imagery, and then you can be able to just validate the data before you actually use it, so that for most of the time we are using it for operational purposes to inform our governments, our policy makers and so on. So you want to provide data sets that are of very good quality, and you are confident that they provide a good information that is reliable and can be used for decision making. So those will be my recommendation. Look at the validation report, look at the representativeness of the data over your country. If it's not that good, then go ahead and validate the data yourself.
That's quite good and interesting. I can see a comment. The comment is that it's quite interesting that you mentioned the use of generative AI for this type of research. I know traditionally some academics are not keen on these tools. And that is quite true. So this would be off the chart. I think probably I'd be throwing in the water, but what would be your recommendations in terms of advocating of more use of these tools, of generative AI? You've mentioned things like using ChatGPT.
Yes, so it's a quite tricky question as an academic myself. So my thing is, these tools are not going anywhere, right? And they are really meant to make your work easier. So for example, if you're looking at writing documents using ChatGPT, the information on specific or specialized areas such as your remote sensing and land cover change and so on might not be that good, because it pulls out, or it has learned from the data coming from the websites and so on. But there are various tools that are very good for research purposes, that are developed specifically for research purposes, that will allow you to actually put in your PDF documents, for example, the research articles, and then it will learn based on those articles and then give you responses that you're looking for from these articles. So this takes out hours and hours of work that you would have put in reading these publications and you can be able to extract data much easier. For example, if you're doing like something like systematic literature reviews, you can be able to actually extract information on which authors used Landsat, for example, for this particular years for land cover change detection. So these tools shouldn't be viewed as replacement of humans and academics and so, or education even. They are meant to make our lives easier, even though even when we use them as well, we still need to go back to say, to validate, right? So in my experience, particularly when it comes to the students, it's very critical to still learn the basics and the fundamentals before you actually employ these tools. Particularly because if you are just using it without having the place telling you the truth or not, and sometimes, for example, with ChatGPT, you can ask it to give you references, and then it will give you incorrect. It will generate references that are not existing, basically. So you still need to go and validate. So they will be very beneficial for people who are already experts in the field. And yeah, so I am obviously embracing the LLMs and encourage everyone to actually use them, particularly for guidance. And so, for example, if you wanted to come up with a layout for a publication or for a presentation even, you can ask it to do that for you, and then you can refine it based on your own knowledge. So I feel like these tools will eliminate a lot of basic steps, time-consuming steps, and allow us to be able to think about the critical content and be more innovative, because they themselves cannot be innovative. We still need human input for that innovation to take place. So if we eliminate these repetitive tasks and that are time-consuming, then you are able to put much focus on the innovation side of things.
Thank you for that comprehensive response. I think Lakshmi, you wanted to add something to that as well.
Thank you so much, Patricia. I mean, he has actually covered whatever I wanted to add on. I just wanted to mention a kind of comment on like use of how these technologies are evolving, and now that there are like geospatial foundation models, there are climate models, there are like digital twins where they are incorporating the interaction of these kind of AI technologies or generative AI context specifically. So I just wanted to add on, like, how do you feel about this kind of technological evolution, and where do you see like the future of geospatial domain, or let's say like what is there in future for us to focus our research on when we talk about use of technologies in our domain? Thank you.
Thanks for that. Yeah, it's very exciting. The future is very exciting and it's rapidly developing. And I mean, this field has been driven mainly by the technology. So with the availability of new sensors, new algorithms, new information extraction approaches, then I mean, is really developing very fast. So this is an exciting time. And in terms of research, of course, we want to start looking at how and playing around with these tools to see how they can actually benefit, but also contribute by training some of the algorithms for people who can, and also if you do not have those technical skills, you can always partner with people from be able to actually come up, solve the future challenges. So one of the critical things in this geospatial science field is that we have these great products and algorithms, capabilities, and so on, but they are sitting inside research papers, right? So most of the time it doesn't get to the people that we want the information to get to. So this is because it's not really obvious. If we think about image interpretation alone, which is a very basic thing, but if you give it to the first year students or school going students, because it's presenting a different view from our normal horizontal view, they suddenly cannot be able to differentiate between the different features, right? So you want to make that information more accessible to an extent that even non-experts can be able to interrogate and use those particular products. So I feel like these tools will really help us in doing that, and help us to actually penetrate the market in terms of this technology being used for everyday purposes and for anyone to actually understand what we are doing. Because for most of us, our grandmothers don't really know what we are doing, and it's very hard to explain to them. But if it's much easier, it's relatable, it can be interrogated with a language, for example, asking these geographical questions: where is what, how many airplanes are there in an image, then it just gives you an answer, pulls out the image, and then count all those things. So what I've noticed is that most of us as scientists, we are fixated on the beauty of the algorithm running behind, the deep learning algorithm that can be able to delineate or segment this image. But that's not important, actually. What is important is the information that's going to come out. Is it usable to the user? Is it what the user wants? Can it enhance or improve the operations of the user in different contexts? So that's really where we want to get to. And I feel like this code technology is going to take us there.
Okay, thank you so much, Dr. Mahlatse.
And I feel like, okay, maybe I did not answer your question fully, but in terms of the research, okay.
No, sorry.
So,
I think it's my
validation
internet.
of this product is one of the, oh, okay. I was saying in terms of the research areas, one can look at validation of these products and further improvements. And also when this, geospatial geo-LLMs are becoming more accessible, we want to check if they are actually providing good accuracies, and then what can we do to actually improve these accuracies.
Okay. Okay, sorry for that interruption. I think my internet was quite slow. I thought you'd finished. I can see this is a very interesting topic. And thank you so much, Dr. Mahlatse. I would request if you could please put your email on the chat. You can put your email on the chat so that anyone who wants to get in touch with you can always email you and continue with this conversation. I'd like to also thank Dr. Yoksa as well for attending and making a presentation. And for everyone else who was able to join, thank you so much for joining us for this second webinar. You can look at the ISPRS website. There are different technical commissions. So this is Technical Commission 3. And there are various technical commissions that deal with various topics and areas of focus. Our working group as well is 4, And there are different working groups that have different focus. Our focus is on land use, land cover change detection. I'd like to hand over to Laxmi as well. Thank you so much, the ISPRS Student Consortium, for supporting us greatly. And for anyone who is interested in joining and knowing more about ISPRS, I think Laxmi can give you more information.
Thank you so much, Patricia. First of all, I would like to thank both of our speakers for their excellent presentation. And it's good to see that the presentations and research are focused towards and are also incorporating recent technologies that are being used or that are in this course. So I really appreciate it. And talking about the membership, I would like to mention here that ISPRS Student Consortium is the student and youth representation of ISPRS. And if you are a student in any phase like undergrads, masters, PhD, you can be our member for free simply by filling up a membership form that I think hardly takes like 2 minutes. You just need to mention about your affiliations. And then if you are above 35 and want to get associated with ISPRS, you have the options of free individual membership through ISPRS. So basically ISPRS and ISPRS SC includes both kinds of, like all kinds of people. Feel free to go to our websites, feel free to apply for memberships, and we have opportunities for summer schools, webinars like this, tutorial sessions, and also lots of travel grants to attend different symposiums. Just to mention here, I think the day after tomorrow is the deadline for Dubai Geospatial Week happening in Dubai, and there are also opportunities for travel grants. ISPRS Congress is also taking place. There are lots of events happening in person that you can attend by applying travel grants too. And yes, that's all from my side for now. And maybe one more thing to add on is recently we have launched the concept of ISPRS SC student chapter, and that is basically to have a kind of chapter in local universities so that we can connect ISPRS community directly with the local universities without having any kind of gap or bridge in between. So if you want to form student chapters in your university, you can contact us, or you can have a look on our websites, and you can let us know if you find any difficulties in our guidelines, or if you'd like to form it in your universities. We'll be happy to help. And with that, and with a small information that next week we are going to attend ISPRS Technical Commission 3 symposium that is taking place in Brazil. So if any of you are attending it, you can come to our booth, and we'll be happy to interact with you more in person. Thank you so much. Over to you, Patricia.
Okay, thank you so much, Laxmi. And thank you to our presenters and attendees. I would like to end the session, and I would like to wish you a great day, evening, as well as morning. And hopefully we'll see each other soon. Bye.